In this video, we're going to go over waiting times, okay? Something I like to call waiting times. What is a waiting time? Well, it's a problem where you have a function and you want to know when it's going to take a particular value. So for example, you have a function f of x and you want to know when it's going to equal 5. So what x will give you f of x equals 5. In our particular case, since we've been working with exponential functions, we've been calling them p of t, and we usually think of the variable t as time. So when we want to know, if we want to know when p of t is going to equal 5, then what we're asking for is how long do we have to wait until p of t equals 5. All right, so that's why I call it a waiting time. Now, since we've already done a lot on exponential functions, there's really nothing to introduce here or any new tools. We have everything we need, so let's just get right into the examples. So consider the scenario. You take some medicine and you want to know how long you have to wait, all right? How long you have to wait until only 30% of that medicine is left in your body, all right? So it's going to dilute inside your body and you're going to wait some amount of time until finally it gets to 30% left. All right. So let's assume that you took an initial amount of P0, and notice how I'm not specifying it because you'll see it doesn't matter for this problem. And think the medicine dilutes continuously in your body. That's important because, well, that's what justifies the use of exponential functions. And the rate at which it's diluting is 0.2% per second. All right, so let's bring all this information together and answer the question. So how long until the medicine in your body is diluted to 30%? Let's translate that into a math equation. So we want to know how long until P of t, all right, that's the amount of medicine in our body, or whatever, your body, is 30% of the initial amount, okay? So 30% of the body, 30% of the medicine is left in your body, right? So how long do we have to wait? That means solve for t. Okay, so P of t, well, we know all the exponential functions look like P0, that's the initial, times e to the r, the relative rate of change is 0.002, but because it's diluting, we know it's negatives, and that our exponential function is decaying. So it's a relative decay rate, and then we have t in the exponent as well. This is equal to 0.3 P0. And so now you solve for t. Notice that you can cancel out the P0, so there you go, it doesn't matter what the initial value is in this problem. And then you want the t to come down, so what do? You take ln of both sides and you get negative 0.002 times t is equal to natural log of 0.3. And so you get t equals natural log 0.3 divided by negative 0.002. And if you plug that into your calculator, you get 601.9864, and the units are seconds. Okay, so there you go. There's the answer. So you have to wait roughly 10 minutes until only 30% of the medicine is left in your body. Notice how we had to use some keywords here like dilute. So that is what told us that we were going to have a negative value for r in our exponential function. In other words, that told us that our exponential function was going to decay. So again, just right here, that was an important word. And then what you'll notice, okay, something you should do right after this video, what you'll notice is that this was very similar to a half-life doubling time problem, all right, the way we did it. Except in those problems, this 0.3 was either 2 or 1/2. And that's the only difference. Okay, so let's do another example, but this time I want the initial value to actually matter. All right, so consider this scenario now. All right, you have a single dollar, and just for, S and G's, you go to the bank and you deposit it. You deposit $1, and you want to wait until it becomes $1,000. And so the question, a natural question to ask in this case is, how long do you actually have to wait? And let's say that this bank that you're depositing it at deposits things, compounds the interest continuously, at an annual rate of 2%. All right, so with all that information, let's find how long you have to wait until $1 becomes $1,000 at this bank. Okay, so as soon as the computer is willing to do that, we will do that. I promise you. I promise you. Okay, so P of t should equal $1,000. Okay, how long? That means we have to solve for t. What is P of t? Well, it's just the initial amount times e to the, well, in this case, it's an interest rate problem, so our money is going to be growing. That 2% is positive, so it's 0.02 times t equals 1,000. We want to solve for t, so what should we do? Well, we could ignore the 1, dividing by 1, whatever, doesn't matter, we could just ignore it. We take ln of both sides, and we get 0.002, 0.02 times t equals natural log of 1,000, and so therefore t is equal to natural log of 1,000 divided by 0.02. And you plug that into your calculator and you get 600, whoops, that was the previous one, 310.73. Oh, but guess what? It's years, the units. Okay, that's what t is equal to. So unfortunately, you will not be able to see this $1 become $1,000 in your lifetime, or find deposit more money, or find a better bank with a better interest rate, or that's just going to be, that's going to be put away for your grandkids, or rather your maybe grandkids. Okay, so this problem, the initial value mattered. So this 1, of course, if we deposited a different amount, then the time would change. But again, it's very similar to, the structure of this problem is very similar to the doubling time and half-life problem. So you should definitely, after this video, compare these problems with those. And another thing you should do is just change the numbers around and practice this procedure. So and see and try to get good at it. All right. So that's all I wanted to say, and that is the end.